Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture 43 of module 9, which is on electrodeposition. As the name suggests, this is a very age-old and a very well understood and utilized industrial practice to produce thin layer onto the surface as a measure of protection for decorative purpose, even for various functional purpose. So for example, if you imagine a water filter, so on the base we load the ceramic element which actually acts as the filter for the water. So water passes through this tube and goes through the ceramic membrane on top of it, and through those small holes or gaps or the pores, water can pass through, water molecules can pass through, but not the insoluble compounds and also certain bigger ions. So they get filtered out and the pure water comes out. So this is a metallic hub on which the filter is loaded, but various aggressive ions come in contact with this metallic hub or the base and leads to corrosion. Now, if there is no protective layer, then it leads to aggressive quite an aggressive amount of corrosion damage, and in the process these initial pits and damaged parts can connect with each other and form a crack. So we would not like that to happen, so the metal surface is coated with certain anti-corrosion deposits, typically a metallic coating, and this is possible by electrodeposition. So in the process of electrodeposition, we need an electrolytic bath which will allow dissolution of the particular salt, and also will allow metallic ions to be dissolved from the anode and be transported through the electrolyte to the cathodic side, whereas the anions from the cathode will move towards the anode and then gets liberated in the form of gaseous bubbles or vapors. So electrodeposition or electrochemical deposition or electroplating, these are all names routinely used. They mean exactly the same process. Essentially allows deposition or coating of metal by reduction of cations, and this is done through direct DC current or direct electric current. So the bath contains electrolyte and 2 electrodes. So we have to supply electricity from outside by way of a battery, and we can of course measure the current that flows outside the circuit. So essentially the cations move from anode to cathode, and outside the circuit, outside the bath, electrons flow from anode to cathode. And in the process, the circuit is completed, and you can measure the amount of current using this ammeter which is connected in series with this 2 electrodes outside. So these are the components. The solution is very important because that allows the level of dissolution of the ions, and the anode, which is a positive electrode, can either be a dissolving type of an anode where the metal value gets dissolved into the electrolyte, and that's how. So if we want electroplating, then either the salt should carry that desired ion, or the anode should contribute that ion. So either it can be an active anode where the metal dissolves, or it can be an inert anode where it simply acts as an electrical electrode, just as an electrode. So we are very much used to seeing such good chrome plating or nickel plating or gold plating or zinc plating. This is basically electroplating of zinc. So in all these cases, electrodeposition, these are all done through electrodeposition process, and that uses an electric current. So it is not chemical deposition, not dip coating. It is basically a process where current flows outside the electrolytic bath, and inside the bath, the conduction is not electronic but electrolytic. So electrolytic conduction within the bath and electronic conduction outside the bath. One can also do electrophoretic deposition or under potential deposition, where the potential applied is actually slightly less negative than the equilibrium or nurse potential for the reduction of the metal. So we are aware of, this is the guiding principle, we are aware of the Faraday's law, which says the amount of electrochemical reaction that occurs at an electrode will be proportional to the electrical charge that passes through the cell. So the reaction or the quantity of metal deposited will be proportional to Q, the electrical charge, and Z is the proportionality constant, which is called the electrochemical equivalent. So since the charge is current into time, so W is ZIT. So this basically allows us in unit condition, when we apply unit current and unit time, we can calculate what is WEQ, or that equivalent is the so-called Coulomb, the total charge that can pass under unit condition. And this is how we can actually calculate what is the amount of metal that we can deposit onto the cathode. So as I said, this is the positive electrode where, for example, copper or any such metal of interest gets oxidized, dissolved, and joins the aqueous solution or the electrolyte. And this is the negative electrode where these cations or the positive ions get attracted. And so this is an oxidative process and this is a reductive process where copper gets reduced and get deposited onto the cathode. So this is how we actually can create a copper coating on the cathode of a particular composition. So the process is that of deposition. The mechanism is based on deposition, unlike diffusion. Of course, surface diffusion plays a role, but unlike the previous lectures wherein we discussed diffusional coating or coating due to chemical reaction onto the surface, here the coating is due to deposition method, but from an aqueous bath or an electrolytic bath, and necessarily by application of impressed current or electrical current. So the important processes that involves is the ionic migration, the ionic transport, the electron transfer outside the electrolytic bath, and also electron transfer for ionization, oxidation or reductive reactions and their transport. But this happens through a so-called Helmholtz double layer. So essentially, if we imagine this is the cathode, the negative electrode, then we expect the cations to arrive from the anode towards this electrode, and when it arrives, initially it basically is surrounded by a hydrated layer because of we assume this is an aqueous bath, so the water molecules will be surrounding these metal ions like here. And when they arrive, they basically pass through, the concentration gradually changes. So initially this is a low concentration region, and then finally when it comes to the inner Helmholtz layer, so this is typically the double layer, the Helmholtz layer, and when it arrives close to the surface of the cathode, then the concentration is the highest. In other words, these red ones, which actually are the cations, they actually, the concentration of them will be highest near the cathode surface. So and when they arrive, then these ions, they get reduced, and then they become neutral atoms, and these neutral atoms now are in a position to get adsorbed to the surface. So it's like loosely bonded atoms, and hence they are called adatoms. And these adatoms actually can move very fast along the surface through a process called surface diffusion. So what we do generally in case of electrodeposition process is to apply a direct current at a steady value. So this is a constant current mode, or we can apply actually a constant current mode or apply a constant potential mode. So if we apply constant potential, then the current, then the applied potential difference is the same, constant throughout the process, or else we actually can vary the applied potential by pulsing to higher level and then bring it to lower level. So this is the pulse mode and this is the continuous mode. So typical factors, the controlling factors which actually influence electrodeposition process, the most important is the current density, because current density is constituted by the number of ions that arrive at the cathode. The nature of anions or cations, that is, so kind of electrolyte we are using and the active or passive anode that we are using, the bath composition and the temperature, the solution concentration, the power supply, whether it's a continuous mode or what kind of a waveform we are using certain filters or modulators. Then if there are impurities present, sometimes we actually add certain impurities as additives to make sure that the arrival of the ions are actually follow a very uniform rate, and so that the deposit that forms is also uniform. Also the physical and chemical nature of the substrate surface, including its topography and so on. So the concentration, the flux that arrives is highest at the metal surface, at the cathode surface, and this is the inner Helmholtz layer where we have the densest packing of these cations. But far away, initially, so within the inner layer, Helmholtz outer layer, they'll be linear, but far away from the cathode surface, the concentration is fairly low. So it decays exponentially beyond a certain distance from the cathode surface, but very close to the cathode surface, it linearly increases and reaches the maximum at the surface. And at the surface, we have these adatoms which gets adsorbed to the surface. Now, why are they adatoms? Because we have to understand for a while, if we consider this tiny little block as a single atom, just for argument's sake or for our better understanding, let's say we have a surface groove, or in other words, we have a vacancy here. So if this surface, instead of being atomically smooth, instead of that, if it contains a groove here where this block can perfectly fit in, either here or here, so this block, instead of staying here onto this flat terrace, if it tries to fit into this groove, then this will be energetically more favorable. Why so? Because for every such new block arriving onto the terrace, we actually end up creating 5 new surfaces, 4 on 4 sides and 1 on the top, whereas the bottom one, of course, is replaced by already an existing surface. So this is energetically unfavorable situation. Compared to that, if this adatom manages to flow in to this groove, then it actually ends up creating only 2 new surfaces, which is the top and the outer surface. Whereas for the remaining 4 surfaces, they actually are not creating new surfaces. The remaining sides, they can match with an existing groove and actually does not amount to creation of new surfaces. So energetically speaking, we know very well that creation of new surface is always energetically unfavorable because it raises the Gibbs energy of the system. So it is energetically more favorable that the adatom either gets attached to a ledge or a kink or goes to a groove like this, instead of staying as a loosely bonded entity onto the surface. In fact, these kind of atoms are more likely to go back into the solution than getting attached to the surface. Now, in such processes, we actually have to understand that the electrodeposition is a process by which we allow cations to arrive onto the cathode surface, and the growth of the deposit or the deposited layer will depend upon the rate at which these atoms arrive, but more than that, the rate at which these atoms actually get adsorbed to the surface, becomes a part of the cathodic surface. So, to ensure that, we actually can use either a unipolar or a bipolar system. So, typically a unipolar means that the direction at which the ions arrive during the cathodic or anodic cycle, they are the same. Whereas in bipolar system, which typically, so unipolar means we basically are using a pulse current, all right, but the pulse is in the same direction. In bipolar mode, we actually use a situation where there is a reversal of the direction in which the pulses are happening in the anodic and the cathodic cycle. So, typically in the unipolar mode, the current will depend upon the Jc, the current density, the peak pulse current density, the pulse length, the duration of the cathodic length, and also the interval between the pulses of the cathodic. So, typically if we create a waveform like this, then let's say this is the cathodic part and this is the anodic part. So, here we are applying a situation where the reversal is absent. So, we have a unipolar current direction. So, the current is always applied in this direction. So, the average current density is measured and expressed in such pulse current situation by this expression, where Jc is the pulse current density, Tc is the pulse length, and Tp is the interval. And this is how we actually also can calculate the total duty cycle, time for every duty cycle, through such expressions. And this is the expression for the average current, which is Jc times the duty cycle. On the other hand, in case of a bipolar current situation, so we basically use a particular train of pulse reserve waveforms, so like pulse reserve waveforms, and cathodic, so which in turn will depend upon the Jc value, the cathodic current, cathodic peak pulse current density, like here, will depend upon the cathodic pulse length, also like here, and also anodic pulse time, because now we are doing a reversal. We are applying the pulse in opposite flipping cycles. So, in addition to the cathodic pulse length, we also have to worry about the anodic pulse time and the anodic current density. So, as a result, the J average and the total duty cycle time in case of pulse reverse current waveform is now changed, is different. So, you can see that the duty cycle time for unipolar current has this expression, whereas the similar duty cycle time for pulse reverse current forms is different, and hence of course the J average value also will be different here. So, when we use pulse current, then the deposit quality actually can be fairly different and actually improved depending on certain conditions. So, during the deposition, if the atoms continue to occupy the pre-assigned positions or locations in the crystal lattice, or in other words, if it increases the length or the volume of the existing lattice, then we say this is an electrocrystallization process, and the pulse current will control the physical and mechanical properties that follow of the deposit. So, the deposit thickness or the nucleation rate will be proportional to the current density, and usually high current pulses produce deposits with reduced porosity or smoother deposits and finer grain size. And this happens because of desorption of impurities and also possibilities of renucleation on the deposits. So, formation of new or smaller crystallite grains happen because of the heterogeneous nucleation process. So, essentially if I have a surface and I have certain heterogeneous sides which are provided by these impurities, then obviously the nucleation rate will be higher and will happen only on this preferred side. The grain size also depends on the duty cycle. That means duty cycle in turn controls the current density and hence the number of ions arriving per unit time, per unit area. It also is dependent upon if there is low carbon or nitrogen content, that means a low interstitial element content, and also low stress. In both the cases, the ductility of the deposit is better and so is the electrical conductivity. So, particularly when we are depositing copper, silver, even nickel, then we are interested in also maintaining high electrical conductivity, and in such cases we have to allow a situation where the residual stress that we develop on the surface during deposition is least and also the impurity pickup is the least. So, in pulse or pulse reverse plating, which basically is not a typical constant voltage DC deposition, in case of DC plating, we use a constant current, and hence the rate of arrival of metal ions, they depend on their diffusion coefficient through the double layer of course, and also depend on, which in turn depends on the electrode to surface part spacing and agitation, the bath agitation. In contrast, when we talk of pulse current or pulse reverse plating, not a continuous mode, then we use a modulated current waveform, and this actually can lead to a better leveling of the deposit. So, the surface topography is better, porosities are less, and also contamination is minimized. So, these are all useful things, and the morphology of the metal deposit that we create usually is better, because I said already that the topography is better compared to what we get in case of a DC plated deposits. But to create pulse current or pulse reversal current, we actually have to use complex waveforms, and this is generally created by pulse rectifiers, and the waveforms could be unipolar in one direction or reversing direction or variable directions or so-called bipolar pulses for the cathodic and anodic cycles. So, on the whole, the structure and properties of the deposits that we create, ultimately we are interested in creating a deposit which gives us the right kind of microstructure and properties. So, that will depend upon the nucleation and growth rate. So, the atoms arrive, they create a crystallite on the surface and the crystallites grow. So, both nucleation and growth rates are important, and that not only controls the crystallite size, but the morphology and several other mechanical and functional properties. So, they depend upon several factors, and these, like the bath composition, the current, the rate of arrival, then impurities absorbed or nucleation sites available, agitation, the diffusion coefficient, the thickness of the double layer, and various other factors. They in turn will control the microstructure, the phase aggregate, the morphology, size, even texture, crystallographic texture. So, we have to worry about there are two ways actually we can think of the amount of deposition or controlling the amount of deposition. The current efficiency wise, essentially if we say that the amount of metal deposited, if we expect that the entire amount of metal is going to get deposited, that's an ideal situation, but the amount of current, the amount of ions arriving and the amount of ions depositing, they are not necessarily the same. So, as a result, there is a ratio between the amount of metals deposited to the calculated or the theoretically predicted number of ions that should arrive. So, this ratio is the current efficiency, and current efficiency is basically, it reflects the total current that generates the desired product. Now, so the fraction of the total current that you expect, if all the ions get converted into the deposit, then of course that's the maximum efficiency, but that doesn't happen. The real amount is MA, so MA over MT, which is predicted by the Faraday's law, is the so-called current efficiency. So the overall amount of the chemical change for a given quantity of electricity passed can be determined by such ratio. So cathode and anode efficiencies, in case of ideal situation where the amount arriving and getting absorbed is the same, then the cathode efficiency will be equal to the anode efficiency, which is not true in case of real situation. In case of real situation, we have to worry about the cathode efficiency, and the cathode efficiency is dependent upon the electrolyte or bath composition, the concentration of chemical components, pH, agitation, current density, and so on. For example, the current efficiency, what we were talking about here, typically for nickel plating is nearly ideal, whereas in case of chromium, it is only about 20–30%, fairly small, fairly low. So that means the nature and the permeability of the double layer that we create, the Helmholtz layer, also depends upon the exact nature of the ions. What does the bath do? It does very important job. It basically allows the electrolytes, ions, the respective cations and anions to be transported through it. Typically conductive electrolytes could be, say, nickel sulfate or boric acid or nickel chloride. For nickel anode dissolution, we use certain promoters. We may also use the bath helps to control the buffer at the pH level. And I mean, we don't want the bath to become too alkaline, so maintain certain pH level. We probably will use boric acid or certain other controlling agents. We may use additives which actually can help better nucleation and making the surface smoother and also reduce the stress level. The bath provides the electrolyte to conduct electricity, basically the electrolytic conduction or conduction of the ions. It also is the source, it provides a source of metal which is going to get dissolved, going to get plated. So the dissolved cations, they move through the bath. The bath allows the anode reaction, which is basically the process by which the anions evolve out of the, convert into the gaseous molecules and then evolve as oxygen molecules or some other gaseous product. It wets the cathode surface so that the cations arriving at the cathode gets adsorbed to the surface and allows good adhesion. It also helps stabilize temperature because of certain circulation within the bath, either externally driven or simply by various osmotic processes. Can also act as a heating or cooling bath. So the bath is a very important aspect of the electrolytic bath composition, is very important, and for depositing nickel, these are the important attributes that we have to worry. So the objective generally is to improve the corrosion resistance, to reduce friction, to improve heat tolerance, and these are the various forms of application. Say, for example, in storage applications as catalysis, for separation, as sensors, also as templates for creation of certain crystallites. Automotive parts, decorative metalwares, jewelry, engineering components, load bearing or simply decorative, printed circuits with providing electrical contacts, and micro parts as in MEMS. All these are the applications of electrodeposition. And as you can see that these are the decorative pieces. This is chrome plated, this is silver plated, gold plated, copper plated, again silver plated. and the appearance, the aesthetic appearance is very, very important in all these cases. So the typical metals which are very routinely used for electrodeposition are zinc, nickel, tin, copper, chromium. We also heard of some precious metals like gold, silver, even platinum, and so on. The applications we already have discussed: decoration, protection, electroforming, enhancement of certain functional properties, and so it can be on wider surface area, not so important, not so sophisticated applications. It can also be in very specific and sophisticated applications, as in context of the printed circuit boards. So this is just an example as to how the loading in the bath affects the corrosion current or the protection. And this also, say for this, in this case we are talking about a zinc manganese coating, an alloyed coating. So one can refer to this particular reported literature, and this will show that if we use, for example, two different current densities of, let's say, 40 and 60, then obviously the corrosion protection is different in these two cases. The breakdown potentials are at two different levels, and the corrosion current density, of course, is going to be higher when we have higher amount of ionic loading, when we have lower amount of ionic loading. When you have higher amount of manganese deposition onto the surface, then the corrosion current is higher and the corrosion is lower, and the corrosion protection is better. So what are the common metals that we deposit as in electroplating? What are the objectives of electroplating or electrodeposition? What are the advantages? What are the factors that affect? What are the different modes of electrodeposition, pulsed mode or constant current or constant potential mode? Why we generally use direct current for electrodeposition, and when we do pulse mode, what is the mechanism and what advantages do we get? How do we maintain or improve the plating quality and reduce porosity? And this pulse reverse mode, what exactly is the mechanism and how does it improve the surface condition? So one needs to also refer to these areas. Thank you very much.